Linear programming is a wonderful tool for trying to maximize a good outcome or minimize a bad outcome when you have a number of linear constraints. In this video, I'll work through a problem that kind of illustrates the power and capability of the linear programming tool, as well as how to use it. A school board is investigating various ways to maximize the number of students that can successfully graduate given an available budget and some other constraints. So the first step in trying to solve this problem is to try to convert the constraints into mathematical equations. So there are 5 constraints in this paragraph. The first constraint is that there's a budget of $50,000 and teachers make $1,500 and aides are paid $1,000. The second constraint is really what the thing you want to maximize, which is that the board has found that teachers can help 8 students graduate and aides can help 6 students graduate. So how do we maximize the number of students to graduate? The third constraint is that there's a requirement to maintain accreditation of a minimum of 12 teachers and a minimum of 20 faculty and a ratio of at least 2 teachers for every 3 aides. All right, I'll get this page set up so that there's a little space and we can put the equations that match each of these constraints. So let's let teachers equal capital T and teachers' aides equal capital A. Then when we create the first constraint, we can say that the $50,000 budget will be $1,500 times the number of teachers plus $1,000 times the number of aides equals the $50,000 per month. The second constraint is really the thing that we want to maximize, and that's that we have teachers can help 8 students graduate a year and aides can help 6 students graduate per year. So there must be at least 12 teachers, so T is going to be larger or equal to 12, at least 20 faculty, so T plus A is going to be larger or equal to 20, and a ratio of 2 teachers for every 3 aides. So 2 teachers must be larger and equal to 3 aides. Then I think the next thing we should do is put each of these in slope-intercept formats. It'll be easier to graph them. So let's go back up to 1 and put that in slope-intercept format. So that is A equals minus 1.5 T plus 50. And let's see, number 2 is A equals minus 4/3 T plus the maximum number of graduates divided by 6. And let's see, number 4, that would be A is larger or equal to minus T plus 20. And for number 5, that would be A is smaller than or equal to 2/3. Okay, so now we can graph these equations on a graph, the ordinate axis being aides, number of teacher aides, and the abscissa being teachers, or number of teachers. So we know the first point is 33 and a third is 0, and 0, 50. And that is our budget constraints. It's basically the equation that the number of aides is less than or equal to negative 1.5 teachers plus 50. The next constraint is just that the number of teachers must be larger and equal to 12. So that just means T is always going to be 12. And a relatively easy one to draw in there. The fourth constraint is just faculty less than 20, which is represented by the equation A larger than or equal to negative T plus 20. So you just draw a line through the 20 marks on both the abscissa and ordinate coordinates. The last constraint is there has to be at least 2 teachers for every 3 aides, and that'll be a line that's going to go through 0, 0, and rise 3 for every 2, looking like this. Now that we've plotted the linear constraints, it's pretty easy to see all the possible solutions within those constraints, and we can kind of shade those in. It's below the green line to the right of the red line, and larger than the blue line, since those are the constraints. But fortunately, there's only 4 or 5 points we have to check, according to the theory, to identify the maximums. The first 2 points are really easy. It's 0.33 and a third and 0.20. The other 2 are we have to solve 2 equations and 2 unknowns to determine exactly where those points are. So let's do that. So let's start by finding the intersection of the black budget line, and the green teacher versus teacher aide ratio line. You basically substitute for A and solve for T. And we get T equals 50 thirds, and then substitute that back into the other equation, and we get A is 150 over 6, or 25. The next point for the next corner, let's solve for where the minimum teacher line, the red line, intersects with the green line, the teacher aide line. That's just easy. It's 12, and you plug 12 in, and you get 18. The final point is also pretty easy. It's the minimum faculty line, the blue line crossing the minimum teacher line, the red line, and we know that it's always 12 for teachers, and you just plug that into the minimum faculty, and you can solve and get 8 for the number of aides. We're now in a position to solve for maximum number of graduates. This equation here. We could check all 4 or all 5 at the corner points, but since we know something about this line, we really don't need to check all 5. We know what the slope of this line is. It's minus 4 thirds teachers. We don't know exactly where the intercept is, the maximum over 6, but we can find that out pretty quickly. I've drawn here the slope of the line, and as it moves towards the y-intercept, when it hits the first coordinate, either that 50 over 325 on top, or the 0.33 and a third on the bottom, that will give it the max number and the solution. So really, we only need to check those 2 coordinates to get a solution to this problem. So let's check those coordinates and see which one gives us the larger maximum. If you recall, it's teachers can graduate help 8 students graduate a year, and aides can help 6 a year. So the coordinate where T equals 33 and A equals 0 results in 264 graduates a year, and the other coordinate is 283. So there you have it. 283 is the maximum that you can graduate a year. Just to round this out, I'm going to check the other 3 coordinates, and you'll see that they all have lower numbers. That's basically because the the y-intercept equals max over 6, and the y-intercept is going to get to be less and less as the line moves to the left. Linear programming also allows you to really think through some of the constraints. For example, here you can see that the constraint of 20 faculty members really has no impact on the number of graduates. But if you change the constraint that you had 12 teachers and made it 17, you would get a different answer to this because that red line would move over. So mathematical modeling plays a role in many sectors of the world today, from medicine to yacht racing to finance to weather, predicting tsunamis, designing cars. It's a big part of the world today.